This is a variable auto transformer. That is, it's a single winding on what appears to be, or looks very similar to, a toroidal coil, except it's about this big and, say, 6 inches high. You can see the windings inside going over and out the whole way around. This is designed to set primarily on a bench. The switch has an off position, 140 volt position, where this acts as an auto transformer capable of stepping the input voltage up. Switch goes down here, which makes this 120 volt variation. No stepping up or down. 12 amp fuse. And I should say why I'm showing you this. I'm going to convert it from an ungrounded system in and out. The cord's in pretty bad shape. So my intention is to convert this to a grounding receptacle and then replace this with a 3-wire cord. Now, I've never powered this up. I bought it at an auction. It had been out in the rain for about 2 months, or exposed to the weather for 2 months. It was raining when I bought it. The bottom is somewhat corroded, but because it was setting up right, I think it'll be fine. I would guess it's 40, 50 years old. We'll just start by tearing this apart. We'll see what's inside of it. We have a restraint clamp here. And these strain reliefs are normally much harder to get off or out than they are on. See how it deforms the cord? And you can see it's 2 pieces. Put the cord through this notch, fold this half into it, and when you squeeze it, it clamps the cord, creates this offset. This 2-pole AC connector is held together with a screw here. Clamp comes off. Wires pull out. Comes out the front. I have hopes of installing this in here. So I'll have to lose these things and keep these screw holes. Then cut a round hole here something like that. Drill 2 holes through the front and bring this in from the back. This is this one happens to be a Greenlee. Unfortunately, this is 1.5 inch punch and die set. I needed an 1 3/8, but I don't have one. What this consists of is a screw or bolt I'm taking out now. And a punch and a die. Looks like I didn't clean it out after I used it last. Looks like I was punching a piece of clear plastic. In any event, what we do with this is I'm going to put the die on the outside. I have a special bolt with a thrust washer on it. I'll put the punch onto the screw, if I can get it in there. There we go. So I've got it pretty well centered this way and as high as I can go. At this point, all we have to do is tighten this draw bolt. And the problem is these punches, you get above 1.5 inches, have a square, not a hex. Once the bolt's tightened up and you hear it pop twice. When I say pop twice, the reason it does that, it's very easy to get started. When it starts, the two cutting edges, one on the other side, begin to draw into the die, piercing the metal. But as it gets closer and closer to completion, this is the hardest part to cut off. It gets very hard on the wrench. Here we are with the receptacle installed. Now I need to do some wiring and insert the new cord. Now we got to install the cable through the strain relief, push it into this hole. The strain relief, as I said, is made in 2 pieces. They're fastened together so you don't lose them, but now you can always cut wire off. It's very difficult to make it longer, so leave enough wire to work with. This thing then folds down. It's got these 2 projecting legs on it. See them there? And there we go. See how I pushed that together? Now this is better done with a pair of channel locks, but I don't have any at this bench. First thing we'll do is just squeeze it together. That begins to put a kink in the cord. So squeezing it together, you see how it kinked the cord? Well, it's much more kinked inside. Just fish the wires through, and you see it won't fit. It's still too big. That's because it popped back open. Now what we've got to do is grab it from the front, fit it into the hole flush, and then remove the clamp. See, and it will tighten up as the wire attempts to unkink. So there we go. I fastened the wires inside, black to black, white to white, and the green wire fastens to a screw on the yoke. Now I'll put it all back together again. It is all back together. 3-wire cord, original cord grip, Light comes on. So I'm going to turn it on to the 120 volt position. It goes up to 122 volts. Doesn't quite make 140, but it does go somewhere above 120. Now, if you're ever going to use one of these, remember that it's not isolated. So you might ask what a variable transformer does, and then how is it used and why is it used. Here's a standard step-up transformer, if this were the primary and this were the secondary. The AC voltage divides itself evenly across these turns. So if we had 100 turns and 100 volts coming in, we would have a transformer with a ratio of 1 volt per turn. Because there are more turns here than here, we will get more voltage here. How much more? Well, we need to count the turns and multiply by 1 volt per turn. Step-up transformer. Step-down transformer. With this is always being the input. And that's what this is. An input of 115 volts, AC always. It steps it down to 24 volts, AC. Now, the significance of a two-turn transformer like this is that there's isolation, electrical isolation, between the primary and the secondary. And since a transformer is not an active device, a sine wave in equals a sine wave out. But the sine waves are inverted. So with a multi-winding transformer with no electrical connections between the windings, we have electrical isolation and a phase inversion. Here is a transformer with just one winding. The same rules apply. If this is the input, we divide the input over all of these turns equally. And this is the output. We determine the output by multiplying the number of turns by the volts per turn. This is a step-up auto transformer. If we input the voltage here, it becomes a step-down auto transformer. Note that the input and output is not isolated. Therefore, there's no phase inversion. Now this is a step up, if we use this as the primary, auto transformer. Why? Because the secondary has more turns on it than the primary. Now, it includes the primary, but there are more. Well, a variable auto transformer I can vary the number of turns contained in the output. And so if I'm down here somewhere, or like here, the output will be less than the input. The output has fewer turns in it. If I'm up here, the output is more than the input. So a variable auto transformer has no phase inversion, no isolation, and it may be a step-down transformer or a step-up transformer. Now your first thought would be, well, if I hook a lamp, an incandescent lamp, across here, I can use this as a lamp dimmer. And indeed that's true. But probably the smallest capacity-wise variac made in the United States costs at least $75. My 50 amp variac probably costs $1,500, if not more. You can vary the brightness of an incandescent lamp with a dimmer, a wall dimmer. You can get them for $4 at Lowe's. The difference is the transformer preserves the integrity of the sine wave. It may invert it, but it's still a sine wave. The wave you get out is at least as good and maybe better than the sine wave you put in. The output from a lamp dimmer, input a sine wave like 60 hertz commercial power, it outputs a really distorted signal. It's not even representative of a sine wave anymore. So we use a transformer in order to preserve the integrity of the wave. And that's why transformers are used for audio. If you fed audio into a lamp dimmer, turned it up and down, it would just make louder noise.